Before I get started, please don't take this as investment advice. If you are interested in investing, please consult the literature for the relevant regulatory body in your jurisdiction. For the U.S., that's the Securities and Exchange Commission. Thanks. So, with that out of the way, what we're going to talk about today is around what is systems integration, because this is an area and a term that gets used quite a lot, but it gets used in a lot of different contexts. And so I want to give you a sense of how my colleagues and I use it, how I'm thinking about it, and where we bring some of these different elements into play. Scales, much the same. We'll also talk about energy systems. The next sets of examples, I want to bring these in. And when I was working through this talk, one of the things that became very obvious to me very quickly is you want to try to follow a linear flow pattern in a talk to make sure that you're bringing everybody along. When you're talking about integration, that works better sometimes than others, and so we'll do our best to keep this in a linear fashion, but energy storage you will see cropping up in multiple places at multiple points in time along this talk, and so that's part of the reason I think also that it becomes very interesting, because there's a number of different elements in these different systems that have cross points, touch points that we do need to be aware of. And finally, we'll wrap up with some of the, say, maybe challenges / opportunities / summarizing thoughts to try to bring some things together that are more uniform and unifying in theme. So when we talk about a system, there's, again, lots of things we can look at. I've said here system integration. I've used the term systems integration. And when we talk about systems from a chemical engineering perspective, it generally is, where are you drawing your box? And that's usually one aspect of what's going on. When we pluralize this word and we talk about systems, it starts to really get at the fact that we have multiple complex networks talking to each other, each of which has their own function, their own hierarchical structure. And now we're starting to overlay and causing these things to intersect in different ways. And when we talk about scales, the three categories that we normally are looking at, it really comes down to size, length, and time. Those are usually the pieces that we're talking about. And so I wanted to just illustrate a few to give you a sense of not only how I think about it, but also how things show up. So this first one really very much is around sources. So here on the left, we've got kind of the historical view where you've got a fuel, whether it's in liquid form, solid form, gas form, or potentially already converted to electricity and going to a particular source, whether it's, for example, transportation, industry buildings, industry only / power generation. It's very linear nature with some overlap and some coordination, but then moving to a much more interconnected, much less linear type of system. So that's one view on source. Another, when we're talking about geographic networks, this gets back to the length scale, a little bit of size scale as well. And one of the things you'll notice potentially here is we still have our traditional sources, but now we're overlaying some additional ones, like data, additional networks that are talking to each other that have their own structure, framework, that have to be somehow embedded into what we're doing from the energy side of things. So when we're now thinking about what goes next here, we can think about now taking these same fuels, this data overlay, and now driving more of this informatics layer. This is a particular figure from Endler and their energy systems integration work that they do out there. And this piece around, I'm using this one here today because this data to information to insights to decision is something, again, coming back to a chemical engineering perspective, is something that we're very, very used to. And this particular figure on the left is one that has been probably circulating for on the order of 20-ish years or so to really help give the sense of what are some of the challenges and what are some of the layers that each of our research works in. And in a lot of cases, we're looking at one of them at the very short time and length scales, all the way up to, say, maybe looking at a process unit, particularly in the R&D space, or maybe looking more in this space academically. This tends to be more of the industrial section, that folks are looking at. But what I really wanted to focus on today is not just each of these as examples, but how we're starting to tie more of these together, and how from an industrial perspective, all of these are relevant, and we do choose to look at these various scales as we're choosing to solve the problems that need to be tackled today. The piece on the right is a little bit easier to get your head around in terms of just pulling some of the process units together, but it's notionally the same type of thing. So now that we've had this, what is systems integration, what types of scales are we looking at, time, length, size, that sort of thing, I wanted to give just a brief introduction to why this and how this shows up for an international energy company. Because certainly for those of us who are based here, the most visible aspect of our business is our retail fuels network, but it's a lot more than that, as you can see from here. And so again, one of this particular chart is kind of going again from this source view to customer services and providing energy solutions that folks want globally. When we talk about power and where that shows up, on the customer side, it's really around EV charging and sales of electricity, either via our trading networks or directly to large customers. It also shows up in our operations, whether it's directly on some of the electrical power types of processes that I'll talk about later, but it's also in our conventional businesses, whether it's the traditional exploration, development, and production of oil and gas, or also in the manufacturing, whether that's from conventional fuels or more now in our biofuels and bio spaces. So hopefully this gives you a sense from, again, a source, a customer, looking at what is the system integration. But this is still a relatively linear picture. Another way that we've started to look at this picture is from a couple of years ago, it really speaks to the number of increasing actors in an energy system going beyond that enterprise level. Because when we're looking at this particular one, we see not only the assets that I was showing, say, on the previous one, but you're also starting to see elements where things connect to global energy markets. For example, LNG cargoes. You're looking at elements that move beyond the individual customer manufacturing piece here. And so one of the questions, and you start to see actually a lot more electricity here as well that's used, in addition to the data and some other networks. So again, just the additional complexity of these overlays that we're talking about. So what are some of the things that we use, tools, techniques, analytical options to help us make sense of this? And this particular paper was really helpful a lot in summarizing in one spot their characterization of integrated energy systems modeling, again, back to this data decisions piece, and thinking about what are the tools that we've got for the decisions that need to get made over the different timescales and how do these interact with one another. All of these are relevant to the operations that we run today. They're increasingly relevant across these two for the operations that we're running now and looking to run in the future. And so, as a consequence, we do have a lot of work going on through all of these different tools, but I'm only going to spend some time, really more today, talking at this longer end to give a couple of examples, because that's, I think, some of the more interesting work that's has concluded and can be shared at this point. And one in particular, to bring it back to how do we work with the Energy Institute and other folks like that on these large system scale problems, I wanted to just highlight briefly a paper that my colleagues did with Professor Piscopoulos and his team a few years back, looking at how do we take investment decisions in a way that really is effective use of capital in a very highly uncertain type of energy system as it's evolving. So the team was able to develop a very generalized methodology to look at different horizons for mostly the planning and scheduling type of problem. And in this case, we were looking at how do we bring new resources in to serve customer demand for products such as electrolytic hydrogen in a way that allows us to really have a good aspect of making solid investment choices in, like I said, a highly dynamic situation. And so this particular methodology, we were able to use it on this case study, show that if you're able to look across these different time horizons and use various techniques, you can actually reduce your investment costs by a relevant percentage. I think it's on the order of 20%. And so that's highly, highly relevant, especially for the types of questions that we get in our business. So now that we've talked a lot about, I would say, again, this aspect of integration around the different types of things, let's now look a little bit more at what we're talking about when we're talking about evolving energy systems. Because this one in particular, I think we often think about where we are in time as being kind of unique, special, and that sort of thing. But one of the things that the EIA has done the last 3-ish July 4th time periods is shown what the usage of energy has been in the United States since 1776. And I've always liked to go back in time because sometimes you'll see patterns that aren't obvious when you're looking at a particular snapshot in time. And the key takeaways for me out of this chart is, one, we've not had linear dynamics anywhere in this history. We've had a lot of ups and downs for a lot of different reasons. Sometimes it's technology on the demand side for energy. Sometimes it's technology on the supply side for energy. Sometimes it's market forces that are global. Sometimes it's market forces that are local. Sometimes it's other things, none of the above of what I've just mentioned. But this starts to give us a sense of where we are now, what has happened, and how we got here. And to dive a little bit deeper, for example, into the renewable space, because as you can see, you've got kind of an interesting dynamic going on at that end. Wanted to just clarify that in this particular case, renewables is actually a summary of, I think it's about 7 different items, some of which are electricity, but some of which aren't. And so I think, again, really making sure we have a good understanding of what is driving some of these changes, or starting at least being able to see them to be able to try to understand them, is really important. Because again, as we see here, nothing is linear on this chart. To dive a little deeper into the role of technology and how technology and energy are interconnected, I wanted to spend a little bit of time on this slide from our most recent scenarios. Shell has over 50-year history of looking at the energy system through the lens of energy scenarios. And we use this to help guide our thinking. Scenarios are not business plans, but they do give us lenses on the world to help us think through the robustness, direction, and options that we might pursue with a couple of different sets of lenses. And we find that very useful. The most recent ones that we've done are called the energy security scenarios, a little bit of an eye chart here. But the key there is not just the energy security part, but we did choose to update them earlier this year and publish because of the impact of artificial intelligence and other forms of computing power. Because again, coming back to this intersection of networks, data, energy, you can see that in here. And this particular one I also think is really helpful to get a sense of what is this evolution, this evolving energy system, because a lot of the critical signposts that have happened in looking back 15 years, where we are today, and looking forward potentially at what might happen, again, not a prediction, but just a potential given the trajectories that we're on with certain factors at play. What we're really seeing, again, is the emergence of new ways that energy is being both consumed and delivered. And so with this particular piece, it gives us a sense of saying, okay, back to scale. We see things coming into materiality. This 1 to 5% is generally what we consider something is material. We can see it in the energy system as a whole. We're also starting to see the dynamics. How fast are some of these things going? How are they taking place? And that gives us a sense of what's going on. So we've got our size, we've got our time scale, and we also recognize that a lot of these are global. So our link scale in that particular space as well. So now that we've got kind of this evolution and this look, let's take a look at a snapshot of where the U.S. was in 2023 relative to the global energy system. So again, looking at consumption, 93.6 quads. Globally, you can see quad is roughly an exajoule, because that's normally how we measure in some of the other reports. World energy on the order of 620. So you get a sense of how large we're talking. And the reason I like to look at this one in terms of, even though it's a snapshot and it's not showing us the evolution, what it does show us is a few things. One, around the sector usage. Two, around the source and what's going on. And three, the concept of overall energy system efficiency. And what we can see from here is that, again, one of the things, as I've put in the title, useful work is really about a third of what we're doing. And that's really because this is, we have physical limitations on how we convert fuels into useful work. And so that's just inherent to some of the system elements that we have today. But we also can see that, for example, in industry, we have, even though there's a lot of fuel use being used there, it's pretty efficient in terms of where things are going for not being highly electrified. We see in buildings a lot better end use, but you've already taken that efficiency hit early on in that conversion space. So it starts to give you some senses around, okay, if we are changing and we are thinking through what are some of the things we need to consider. So digging into efficiency a little bit more, one of the things that, again, I think was really important to think about is, electricity is the most highly effective form of energy carrier because you can use it for work directly or for heat if you so choose. And if you don't have to go through a fuel intermediate, if you're able to go from photons directly or indirectly via wind, this is a different paradigm than starting with fuel-based systems. Your electrons aren't having that initial conversion step, so you can think a little differently around this. Efficiency is not the only parameter. We'll talk a little bit more about some of the other things around using electricity, but it is a really critical difference. So I want to switch gears now and kind of go back to, again, evolving energy from a demand side versus, say, a supply or strictly a sector side. And up until about 6 months ago, there wasn't really, and there still really isn't, convergence on what is a large load, what is a medium load, what is a small load. Still a lot of discussions around this, but for the purposes of this talk and things I've been working on over the last several months, I decided to use 100 megawatts as kind of my dividing line, because you start to see, say, an outdoor stadium 5, small town 20, campus CHP, depending on how big your campus is, industrial, and this is more light industry. In this particular graph, they were really looking at some of these EV charging depots that were coming in, again, somewhere in the 5 to 30 megawatt range. And when we talk about light industry, that can be things like, for example, I've got a picture over here from an article from last year around that was highlighting a metals recycling plant in Georgia. And again, we were already starting to see some of the strain, even in this kind of 30 to 50 megawatt accessibility of electron space. So when we talk about now going beyond 100, because EVs, transportation electrification, has been on the radar for several years now in terms of, say, grid planning and load growth, what are some of the other things that we're dealing with? So again, when we think about light industry versus heavy industry and things like that, in this larger load space, when we're talking about light industry, this can be anything from, say, a more traditional, say, enterprise data center versus an AI type data center. I put those kind of more in the 1 gigawatt and north for the large scale ones. But things like battery manufacturing, semiconductor fabs fall into this category. We also have more electrification going on in oil and gas than a lot of people recognize, whether that's on the order of somewhere between, depending on how you count, 300 to 500 megawatts of additional load in the Permian on an annual basis for the last couple of years. Whether you're talking about electrifying LNG, Freeport is the largest that's currently operating in the U.S. But again, we're talking about things that are quite big from that standpoint. If you start now talking about chemicals and refining, you can start seeing some of the other types of units and for scale. And when you start looking at nameplate supply, you can kind of also start to see where this falls. So again, coming back to complexity, coming back to what do we have to think about, what does this mean, how do we start pulling some of these things together? One example I wanted to show, because we talk a lot about data centers, but this was from a newsletter about a month and a half ago that I get, and it was really showing the Idaho Power Integrated Resource Plan. And I liked this one a lot because it had the data center in there, but it also had key research facilities doing work at scale. It had food, it had our semiconductor fab, and it had our traditional chemicals. And I think this is really indicative of a very, very big change, this evolution of how we're thinking about what we're trying to do, where we're trying to do it, and what energy sources we're trying to do it with. And to close, because I've spent a lot of time talking about US-based energy systems and how they're evolving, I want to just finish up this particular section with just a snapshot of where the world is: Middle East, China, APAC, Americas, India, rest of the world, Europe, different forms of energy that are used. Again, this is primary energy demand. And then now switching more to what are the dynamics of a heavy industry from a regional basis, from an OECD and a non-OECD. And apologies, my colleagues, when they wrote this report, did not use the same color scheme throughout, so we have to look at the different ones. But the key here that I really want to just point out is that we do have to look at all of these things through the lenses that matter to the region for the sector of interest. And so this is something where we need back to the tools, techniques, as well as the underlying physical information to really be able to do these analyses robustly to figure out what the solutions are, whether it's for an individual company or for a broader ecosystem. So now I want to talk a little bit about some of the aspects of industrial electrification. I'm going to focus on electrothermal, one example of electrochemical, and interwoven with grids throughout. So when I first started working in industrial electrification, a lot of people were saying, well, why would you do this? This is not what we do. This is not how it's done. But I like to dig back to say, where has the world been? How did we make some of these choices in the past? What was driving some of this? And the fact of the matter is we do have large examples. Not a ton, but some. And so the question becomes, why did we have these? And so, as I mentioned here, it really came down to the intersection of low-cost power, critical products to grow the society at large, because you see things like basic metals, basic building block chemicals in both of these cases. But the last one is the one that really intrigued me, the practical driving force piece, because one of the things that we've talked about, that gets talked about a lot, is just direct substitution. But the reason these four really came about is because either pressure or voltage were the critical driving forces for these reactions versus a thermal gradient. And so keeping that in mind and saying, okay, how did we get here, has been really instructive, because it also starts to help you say, what can we learn from these as we move forward? Because they're also still our leaders today in terms of what are the next steps in how do we run these operations. So in New Zealand, the Rio Tinto plant historically ran with approximately 5% flexibility. It was run on 100% hydro, and about 18 to 24 months ago, they switched to running on a mix of hydro, solar, and wind to be able to better work with the grid as other demands were growing as well. And so what they've been able to do, and what they've been putting into practice since this contract was signed in June of last year, is to be able to go not just 5 to 10%, but go all the way up to about 25% of the total operating plant capacity to run it more flexibly. And so this gives us a sense of, okay, if we are now going to say, how do we move beyond this to some of the other critical chemicals that underpin a lot of industrial manufacturing, we can then start to really ask ourselves in more detail, what is actually going to be required to be able to do this? And so, again, taking a step back and saying, how different is this from what we do, and where are the areas that we need to focus? We talk about flexibility a lot, and we jump immediately to how do we work with the grid and that sort of thing. But if we take a step back, we can also say, this is not new in terms of some of the ways we've designed, operated, and analyzed our processes to be competitive, as well as maintain product quality, and continue to advance some of the technologies that we use. So here are 4 different types of flexibility that are listed: feedstock, capacity, product, and operational. And when we start talking about the energy inputs changing a lot, that's really about this operational piece. And so what you can see on the right is really just an illustration of some of the additional elements that need to be considered, but it's just additional parameters into some of the analyses that we've looked at before. So to highlight again some of the additional differences before we get into how do we abstract the problem to say, what are these elements we need to take into account? I just wanted to touch briefly again on the aluminum versus, say, a refining example. With an aluminum plant, you're dealing with, on the order, usually somewhere of 300 to 700-ish smelting pots. So smelting pot 1, smelting pot N, and anywhere from 3 to 700. And you're talking about things that are on the order of 1 to 2 megawatts each. When you go to the refining side, your N for any particular process is a lot smaller, number one, a lot more range in terms of what size might be and that sort of thing, and definitely not always the same operational time scale. So, what are some of the things that we really think about? One of the key elements for us that we really wanted to help us think through this is how do we talk about the reactor, so the thing that is the most critical to what we're trying to make, separations that support that reactor but are maybe more generalizable, and the utilities piece. And you can see all of these different other considerations. So this is how we've abstracted back the problem and really, again, started looking at how do we take from the process systems engineering community, these are examples from, say, the 80s and beyond, where some of these concepts were first introduced, and how do we introduce them into relevant processes for things that we're interested in. And so for us, the first thing we decided to do is for these now thermally driven processes and thinking about how do we go about making them electrothermally driven, we said, all right, what are some of the key questions that we need to ask? And you can see these elements around not just the operation control piece, but how do we think about it from driving the ground up? Because back to what changes do we need to make when? How do we make sure that we're making investments over the right horizon, of the right scale, at the right time, in the right place? All of these are really critical and have a number of factors that come together. So we took a very generic process looking at, again, reactor, separator, unit operations, utilities, and said, okay, what happens, are there really critical underlying phenomena that we need to consider given this change that we're making, especially when you've got elements of recycle and things in a traditional process that we have, because as I mentioned earlier, industry's really driven a lot of efficiency gains. This has been done to take cost out, reduce energy use, a lot of benefits there. And these are really hard-won gains that we don't want to give back just because we make a particular change. And so when you start thinking about some of the questions that you have to answer, these come into play. And so the first thing, though, that we wanted to say was, okay, what actually potentially do we need to, what is coming out when we look at not just a theoretical, but also a dynamic simulation of this kind of basic generic process where you've got reactor, separator, recycle, utilities. And what we found here, as you can see, is that you effectively have 2 timescales. One is managing in the temperature energy scale, and that's fast, and your material balance is in your slower timescale. Again, not terribly surprising, but the fact that this now you can start to think about this and say, okay, how do we use the fact that when we take out this one piece, when we electrify the heating, so that we're mainly having to deal with the material balance, how does that help us potentially work through some of the product quality benefits, some of the other elements, efficiency that we can capture as well. But when you do that, especially if you're trying to use intermittent energy sources, you do run into the problem that these inputs then become your rate limiting input. And so then the question becomes, do you have a role for storage in these processes? So what we've been looking at more recently is to take a look at, flexible operation without storage, looking at electricity storage, and looking at thermal energy storage. Because all of these have the potential to help us make the best use of our capital investments at any given time. But understanding what that combination looks like historically has really been a product of running a lot of scenarios. And so the question for us became, are there ways that we can look at some underlying unifying phenomenon that help us get better at not just the operation and control, but again, at the design and the sizing stage of what we're doing. And so again, what we started to do was try to normalize some stuff, looking at volatility in energy markets, because again, coming back to looking at what is it that makes sense from an economics perspective, how do we do that? Looking again at some of the timescale ratios, and again, coming back to what's going on in the price dynamics to help us figure this out. And what we found in this particular case, which again, it's a little bit of an eye chart, but the key here is that for electricity energy storage, what we're able to see is that at very, very low normalized volatility, it's not worth it. Just use flexibility in your process. I think that's a very intuitive answer, but I think really being able to show that in a normalized way was super interesting and helpful for us. It also was able to show us that if you're able to look at, this is the effect of capital costs and things, because we wanted to really see, that's a goal that a lot of folks are using for grid operations and things like that. How much of some of these declines is it going to make a difference for our manufacturing processes in terms of growing how much you need? Similarly, on thermal storage, you see more spread. Again, this tends to be because thermal storage is less expensive, so you would default to installing that first. But you do also start to see some important dynamics as well. And again, as we're talking about here, we've got a capacity plateau because, again, it basically said, we'll take as much as you can give us if it's that inexpensive for the 200 megawatt nominal process we had. When we're looking at the frequency side, the key here really is, again, one of the things that we were looking at here is trying to figure out, again, this balance between fast discharge dynamics, low time scale ratios, larger storage, because a lot of things have said, hey, long duration energy storage, we're going to need it, it's going to be really important. And the question for us really becomes how much for, how long, and where, in what form. And so this is really trying to get us to those answers more quickly through some of this modeling of this generic process in a particular market. We were looking at ERCOT, by the way. I realized I didn't include that slide in this particular one. So the question, I think you're like, okay, great, this is interesting, but why do we care? So for us, we're actually starting to implement some of these technologies in our plants now. We have a lubricants plant in China where we've put thermal storage in, replacing diesel-generated steam. So again, that was very much an economics-driven decision with emissions benefits. We're also electrifying one of our plants in Germany. We're redesigning, overhauling a base, well, it was a hydrocracker. Now it's becoming a base oil unit. That's due to customer demand in the region. And we're choosing to use electrification here, again, as much for the product quality as anything, because these particular base oils for the applications that we're using have very strict performance parameters. And so we're able to meet those more readily with the electrification, the heating. So when you talk about what are some of the keys that we're, and where is this going, this is the type of scale, and this is a retrofit of an existing facility. So coming back again to evolving in scales, we still have to make sure that all the utility systems and things are continuing to work. So from that standpoint, it's also been a really interesting project for the folks that have been working on that. I've been less directly involved in this one and working more with my colleagues on a few aspects, but being able to watch this grow from some of the work that we did several years ago to actually being constructed now is really, really exciting. We're also switching from electrothermal to electrochemical, looking at electrolytic hydrogen. This project here, Holland Hydrogen 1, is also under construction in the Netherlands, 200 megawatts fed by offshore wind. Output goes to Shell Energy and Chemicals parks. And again, this really is about how do we make sure that we've got the components in these products that we're selling to customers. And from an electrochemical perspective, we talk a lot about, again, electrochemical processes being a little more native to the types of grid interactions and grid integration, but there are things that we do have to think about at the smaller scale, like the power electronics level. Both of these particular papers are work that my colleagues have done to make sure that, on this case, you've got power quality requirements that are met, looking at voltage sag and how to prevent that, so that you aren't shutting down your equipment unexpectedly. And in this particular case, we're looking at the role, again, of novel topologies so that you can run alkaline electrolyzers within their typical operating envelope for, again, highest performance, highest safety, better economics. Finally, I wanted to also talk about systems from an ecosystem perspective and where electrochemical comes in. Shell is one of the world's largest LNG traders, and this was a slide from our LNG outlook earlier this year. And it's really showing, again, where there is demand potentially for the types of products like what we're calling liquefied synthetic gas, again, tradable, able to go through networks, pipelines, shipping that we're using today. So being able to maybe have complexity at this front end of all the different elements we were just talking about, but being able to use a lot of the infrastructure and things at the back end. These are, again, open questions that we're looking to understand and use the tools appropriately to help us understand and solve and provide the energy solutions that folks want. Finally, I want to talk details about energy storage, because there's a couple of things I think here that, again, really now start to speak to not the large scale-up production ecosystem networks, but very much the small scale, so the very low level on that atomistic and molecular phenomena scale. And we're going to talk about lithium-ion batteries, because that really has fundamentally transformed how our energy systems are working today. And again, this really is also a science and a scale problem, because that was unlocked by work done and recognized in 2019. The three winners of the Nobel Prize in Chemistry, each for their parts of making that system and device work. I put this also here because one of the things, I think it's now pretty well known, but a few years back less so, is how the success at the smaller scale unlocked what we were able to do supply chain wise at the larger scale. That modularization, the learning, all of that had a big role in what happened with this particular technology. And if we talk again about scale from a stationary perspective and integration with markets, we're now really getting crisp in a lot of places around how do we remunerate different services that in the past we maybe didn't have to think about doing as a separate service, because it was just part of how the system evolved through the different sources and fuels that we used. And so getting very clear on this integration of what is the scientific thing that we need physically to make our system run, and then mapping it back to some of these new technologies has also been really, really interesting. And again, as we unlock and unpack some of the challenges, we do recognize that we need different functionalities that are serviced by different technologies. So to really dive into a lithium-ion battery, before we go into very, very small length and time scales, I wanted to talk about figures of merit and how they map back, because when we first started working on our program in this area, on the order of 8-9 years ago now, you can see some of the output of the program at this point in terms of what we've looked at. We really started and said, what is it that we need to be looking at, and how does that map back to fundamental phenomena especially where we don't know exactly how that works, so that we can really start again to think about from the design layer up for the applications that are relevant to us as a company. Shell is, and I don't think I mentioned this earlier, Shell's actually got the second largest EV charging network globally right now, so we're very focused on that, particularly in what we call out-of-home charging. So those are the fast chargers and things, where a lot of these elements start to come into play in terms of what's going on. We're also involved in using lithium-ion batteries for stationary, And some of the key elements that I really want to talk about are at this low end, this low characteristic time scale and length scale. And this is the last example, work that we did with MIT in particular. And this paper came out about 2 months ago, culminating a number of years of work, both from a theoretical, simulation, and experimental perspective. And the key thing to note about this is, historically, when you've got a lithium-ion battery, you've got an intercalation mechanism where ions are moving in and out of a lattice structure network. And the type of lattice depends on the chemistry of the cathode that you're talking about. In a nutshell, our traditional representation of both ion transport as well as electron transport didn't really cover what we would see, especially outside of the regimes where those models were known to work well. And we're talking not small problems, but orders of magnitude types of things. And so what the team was able to do over the last few years is really work into the details of how to couple both ion and electron transfer such that, again, getting a unified view on what is happening, particularly in regimes of interest that are relevant for high power density types of operations for lithium ion. So really the key here that we were super excited to see is that not only does it work for a class of these lithium ion cathodes, whether, say, your spinels, your layered oxides, and things like that, but it works across all of the three major classes and does a much, much better job than some of the other existing methodologies that we have today to characterize. I talked a little bit about this, so let me just do a quick wrap up and then we'll be able to take some questions. One of the things that I think is really exciting for me is that we are seeing a lot of R&D across all of these different stages. But that really does present a challenge. How do we use this information effectively, quickly, for the different purposes that we need to in order to make the decisions that are demanded by whatever role that we have, whether it's commercial or, in my case, or other, depending on your role in the energy ecosystem. We talked about some supply and demand issues. This is specific to Texas here in ERCOT. How do we match this demand growth with supply? We are getting better on the definitions. We're also starting to see things get very, very tactical and concrete. Again, earlier this year here in Texas, looking at what does it actually mean to interconnect a large load. Southwest Power Pool, much the same. So really, I think for me, that also is really showing the evolution of, these are not just ideas that were something that we started talking about a few years back that we're still working to try to see how it's going. There are a lot of implementation things in the works right now that folks in this room and beyond are working on today. So when I think about where are we, there is, we talk a lot about change, things are different and that sort of thing. So as a chemical engineer, I said to myself, okay, how do we really anchor around what are some of the critical things? So at the top, we've got, a lot of these things are changing. We've talked about different feedstocks. We've talked about different inputs. We've talked about increasing complexity. But really taking this aspect of saying, how do we make sure we're defining our system, analyzing it, using the tools, building new ones as we need them? How do we make sure we know energy efficiency is a good thing? We've been using that lever for a long time. How do we continue to use it effectively in these new paradigms? Making sure that this works. Techno-economic analysis for economic feasibility has to be part of the equation across the development cycle. And finally, I haven't spoken a lot about this, but certainly for the technologies that you've seen us introducing, we absolutely have process safety as a key component of what we're looking at. So just to give some final thoughts, again, I think there's a lot that we have a chance to look at that we're growing and learning from a supply-demand standpoint. Research, development, and demonstration continue to be important, and really helping to work at speed and scale are going to be critical to solving some of these issues. And for me, making sure that we've got a multidisciplinary approach, that's been something that has always been energizing. And I'm glad to see that continues to be the case to bring some of these things together. So with that, I'd like to say thank you to the Energy Institute for inviting me. Thank you to all of my colleagues who have supported all of this work, as well as our collaborators, and I'd be happy to take any questions.
Thank you.